Welcome everyone to our presentation on safety guarantees for neural network dynamic systems via stochastic barrier functions. This has been a research collaboration between the University of Colorado in Boulder and Delft University of Technology. The problem considered in this research is as follows. Assume we have some autonomous dynamical system in a safety critical scenario. The system starts from a set of initial states and is moving through some environment filled with obstacles and bound by constraints. We assume the evolution of the system is described by a neural network with some additive noise. Such models have gained popularity due to the power of neural networks to represent complex systems. Additionally, training of neural network controllers can be achieved faster and more easily. The closed-loop dynamics is simply obtained by the concatenation of the neural network controller and open-loop dynamics. We seek to provide formal guarantees on the system's behavior to ensure safety, which for neural network dynamic models is known to be a challenging problem that remains largely unexplored. If it turns out that the safety of the closed-loop system cannot be guaranteed, we seek to synthesize additive controllers. Controllers are only synthesized in regions where unsafe behavior is observed to be minimally invasive. Overall, this paper answers the following research question: how to provide safety guarantees for neural network dynamic models in safety-critical domains. Our method for the assessment of safety is based on stochastic barrier functions, which has two main advantages. They provide necessary and sufficient conditions for forward set invariants, and they allow us to verify safety without having to unfold the system. A function is called a barrier if it satisfies four conditions. The first three conditions are listed here. The first condition entails that the barrier must be globally non-negative. The second condition states that the barrier must be smaller or equal to constant eta in the initial set. The barrier must take on a value of greater than 1 in the unsafe set. On top of that, we have a so-called martingale condition, which states that the expected value of the barrier under the system's dynamics must be smaller or equal to the barrier in the current time step plus constant beta. It follows that the safety probability is then upper bounded by 1 minus eta plus beta times the number of discrete time steps n. We seek to find such a barrier function for our system, specifically focusing our search to the class of sum of squares polynomial functions and use SOS optimization techniques to synthesize the barrier. We must therefore perform convex relaxations on the output of the neural network. We partition the state space and use recent approaches to find linear upper and lower bounds on the output. Since the probability of safety is related to eta and beta, it becomes evident why we seek to minimize these two parameters. In the paper, we derive the barrier conditions as SOS constraints and obtain an SOS convex barrier function that maximizes safety probability. If the probability is above some specified threshold, the system is considered verified. If we need to further robustly maximize the safety probability, we synthesize controllers. Obtaining controllers from SOS class functions generally leads to problems with multiplication of decision variables, leading to a non-convex optimization problem. To that extent, we use the SOS convex property of the function and drive the state of the system to the minimum of the barrier function by minimizing this norm. This results in a simple linear program that robustly minimizes the beta value in each region. The minimum invasive aspect comes into play by identifying the regions of violation and only applying controllers to these regions. Finally, we highlight some of the important results. We performed our methods on 3 of the OpenAI agents and a 4- and 5-dimensional Husky model. We were able to scale up to multiple layers with hundreds of neurons per layer and up to a 6-dimensional system. Some of the results are highlighted here. For the pendulum model, we observed that for an architecture of 1 layer with 64 neurons and 120 partitions, we are able to guarantee safety with 99.7%, and hence an additive controller is not needed. For the carport model, we could guarantee 60% of safety, and hence our control approach had to kick in to increase this probability beyond 95%. The same is observed with the Husky and Acrobat. A sample simulation of the carpal is provided here that shows how the controller guarantees safety. In fact, our control approach was able to guarantee safety of more than 95% for all the models considered in this study. This was a short highlight of our paper. For questions, please visit our poster session or contact me at the provided email address. Thank you.